Right. Hello and welcome to this instalment. I should actually say electricity. Can't even get the topic right, but you know, we'll get there in the end. So, photoelectricity. So, obviously, that is the topic of today's exciting adventures into the world of my mind. So, photoelectricity. Well, this is part of the AQA Unit 1 AS course. Now, we're starting about halfway through, we're starting on a chapter called Quantum Phenomena. There's only going to be a few videos and things to go along with this. So obviously in this one we're going to be doing photoelectricity. In the next one we'll be doing excitation of atoms. And then the third one and the final one, check if there's anything else. And we'll be looking at wave-particle duality. They're the three kind of major topics that we're going to be covering in the quantum phenomena bit. We've done the electricity bit. I'm going to go over the particles. I have created a DVD if you are interested, but I think we're going to we'll see how converting that to MP4 goes. If not, we're going to have to do this. Anyway, that was just a quick introduction to quantum phenomena. So, anyway, photoelectricity. Well, what is photoelectricity? Well, you may know that the word photo reminds you of photons. If it shouldn't, if it should, sorry, if it does, it should. If it does, it's good. If it's, you know what I mean. Just Karen, let's do some physics. So, photons. What are photons? Well, you should know that photons, if you don't, I'm sorry, but photons are packets of light. They're not just something, you know, you're just walking around and you just go, oh, I've just got a sort of tissue here and we're going to call that a photon. Well, it's not exactly a packet of light, it's a packet, but it's not of light, it's of crud. So, photons are packets of light. So, packets of electromagnetic waves, to be more precise. So I'll just put that over here and I'll leave that on here, so if you ever get confused, you can check this out. Packets of electromagnetic waves. So, that's essentially what photons are. Now, we have to ask ourselves, well, how can we relate this to our wonderful topic of photoelectricity? Well, I can tell you down and dandy what it is related to. So, what we're going to be looking at is we're going to be looking at metals. Now, you have no metals have electrons inside their atoms of the metal. So, if we shine light, light, as we know, is packets of electromagnetic waves, which are photons. So essentially, I'm being showered by photons right now. So, let's draw a metal here. Now this is just an enlarged bit, and we're going to draw a few electrons. Obviously I'm going to draw them perfectly arranged, but they're not necessarily always like this. I'm just giving a few electrons here. You're probably not going to look like this in an atom, but obviously they're enlarged and it's just to kind of help you understand it. So we've got our electrons there. Now, as I said, photons, packets of electromagnetic waves. So if we shine electromagnetic waves, so actually I'll only draw one, and then we can, because I need to demonstrate. So we've got our vast array of electrons here. And obviously, as we go down, we've got more electrons. So just put more electrons. Crazy is that? So if we shine a light of just one packet of electromagnetic waves, what's going to happen? Well, nothing is going to happen because we've not given them enough energy to take away, to get away from, to be emitted from the surface. We're only giving them a small amount of energy. So if you can imagine, I don't know, without using something. So if you yeah, if you go to knock down a house of Lego with a ball, you hit the ball at the Lego, it's not going to fall over. But if you hit it a bit harder, then it will. That's the kind of same thing with this. So if we hit it with a small force, or a small amount of energy, which is E equals HF for photons, which I should put that down. So you're teaching myself as well. So E equals HF for photon. So we know the smaller energy the photon is not going to emit. So just going back to this equation, E equals HF. H Planck's constant, F is the frequency, E is the energy. Obviously that tells you Planck's constant is fixed, so it's a constant. You can know that without knowing what Planck's constant is, and the energy depends on the frequency of the wave. So, as our strike hits it, nothing comes off. Now if we add a few more packets of electromagnetic waves, or a few more photons, once we reach some kind of barrier, what we call the work function of the metal, and it's denoted by this kind of weird symbol, we start to get one or two. I just draw one actually, just to make it simpler. We get one. I just draw four. Yeah, because really this doesn't happen, but what we imagine really is that for every photon we shoot at it with the sufficient energy, it produces one electron, or one photoelectron. That's how it gets named photoelectricity, because it's produced by a photon sort of thing. So that's one photoelectron. And we've got four. So that's alright. However, if you give it more than the energy it needs to break free, what's going to happen to that energy? I mean, it can't disappear. I mean, it's come out and it's still got some excess energy from doing the work done to break free, sort of thing. And the song Break Free is not going to start ominously playing in the background, and I'm not going to start dancing, so please don't get your hopes up. You know, flow photoelectricity. Yeah, so we've said there's a certain thing called the work function of the metal, and obviously this is different for different type of metals, because it's sort of harder for electrons to get out certain metals, if you can think of it like that way. So it's going to be a different value for different metals. So if we give it excess energy, so I'm going to draw another diagram here. I'm going to rub both of these off, but just doing it so you can see the comparison. Just draw the electrons on. This pen is starting to go, so if we give it more than energy, these electrons are going to be higher up, if you imagine it. I really need to change the pen. And what we've got here, we've moved them away, so they've got kinetic energy. So this is the kinetic energy of the electron plus the work. No way. Yeah, so that's the I'll go into that later actually. Kinetic energy of the electron there is because it's moving about, so it's got some kinetic energy associated with it. Now, how can we put this into some sort of formula to put this into some sense, if you like? Now, what I'm going to do, just going to give you a moment to pause the video, and I'm going to rub this off so we can kind of come up with some ideas about how we can put this into words, if you like. Hopefully you've done that. So I'm just going to rub out the left hand side. Leave that on there. I'll leave the right hand side because that's more of what we're interested in, really. What I'm interested in. So we know E equals HF. So what we can do is we can surmise that the energy of this photon, which is a starting energy, it's got to be one sec. I'm going to do this and it doesn't work out, I'll have to let you know. But so we've got the kinetic, we've got the whole energy here, and that's equal to the energy to get it out of here plus the energy of the moving particle. So I mean, don't give you this equation in the exam. So the E equals HF, and HF, which is the energy of the photon, is equal to the work function of the metal, which is the minimum energy required for an electron to break free of the metal, plus the kinetic energy, if it has any, of the electron. And obviously, if you wanted to, you could work out K equals half of mv squared. If you know Ke, you know the mass of an electron is 1.6 times 10 to the minus. Oh no, sorry, 1.67. Sorry, times 10 to the minus 27. And you can times that by v squared and work out the corresponding kinetic energy or velocity if you really want to. Generally, they don't ask you to do that in an exam. So we can rearrange this to get the kinetic energy. So the kinetic energy. Sorry if you can't see this. I'm trying to drown the life out of this pen. Kinetic energy. It doesn't matter how you write it really. K equals Q take HF. So these two equal each other. I mean, you can try and figure that out. If you think it's wrong, let me know with some proof, and I'll alter it. Otherwise, I'm fairly sure this is right because let me check. That formula is definitely right. You have to take Q. Sorry, that should be the other way around. I just rewrite the second one. I've done it the wrong way around. Awkward. Sorry about that, guys. So that one definitely is right. Just you take away Q from both sides. So Ke equals H. Oh no, it's Q thing minus HF. Sorry, I think that's right. Yeah, I'm not 100% sure about this one, but this one's definitely... That's not good, is it, if your teacher can't even work out what's right and wrong. Yeah. Right, well, I'll go back and put another introductory video at the start if I find out this is wrong, but assume that is right for now. So that's how we get that equation. Sorry about the mix-up there. So that's pretty much it. So the kinetic energy is a maximum amount of energy that an electron can have, given the Planck's constant, which is given the frequency of the photon. And the work function is the minimum amount of energy needed for an electron to be emitted. So if we've got this equation here, we can work out if the electron is not, if we want the electron to just escape, but we need to work out the work function. So that means it has no kinetic energy. So we could basically write this as being 0 equals work function take HF. So if that equals 0, we can say the work function equals HF. And if we know the work function, we know the... and then you can just rearrange that to find out either the work function... Sorry, let me see if you can see that. So, I'll just zoom the camera in a bit. So you can see that. And now, where you've got the Q, that's a work function, and H is Planck's constant, F is a frequency, and you can sort of work out, you know, if you want to work out the frequency or the thingy, that's quite simple. Now I hope you've got that. It's quite an introduction to photoelectricity. In our next video we'll be going over excitation and deexcitation of atoms, so enjoy. Right, sorry. This is just, I was just finishing off the photoelectricity However, I thought when I did it, I thought this isn't right, that equation I put down wasn't right, because the work function could not be bigger than the energy of the photon if there's going to be any movement and there's going to be any kinetic energy. So you always take the work function away from the maximum kinetic energy. So that's the correct equation in red there. I hope you've got that, and we'll see you in the next few videos.